degree in chemistry at the University of Zaragoza. Then he went for a couple of research stays first at the CNRS, and then UCLA, I guess. Yeah. And then he landed at the University of the Basque Country, where he became a professor in 2002. But beyond all these achievements and research works, he's a key figure in the progress of science in general in the Basque Country. And for instance, since 2009, he's the scientific director of Iker Basque. And just to let you with him, mentioning that all his work was recognized 2 years ago with he was awarded with the Euskadi Research Prize, which is a very prestigious one. So Fernando, please.
Thank you very much, David, for your kind introduction. And thank you, Marek, for giving me the opportunity to share with all of you our recent research on a very peculiar transition from particle physics to supramolecular chemistry. So let's start by formulating according to philosopher Martin Heidegger, is the fundamental question of metaphysics. This question was proposed by Leibniz, and it consists of answering this essential question. Why is there anything at all? Or in other words, why is there something rather than nothing? Fortunately, nowadays it's possible to transfer this very fundamental question from metaphysics to physics, and even more, if as we'll see later on, even to chemistry. So first, let's take a look to the standard model of particle physics. As you know, we can distinguish fermions in quarks and leptons, and bosons, and finally the essential Higgs boson. Fortunately, most of physics and chemistry, at least 5% of known matter, can be described in terms of quarks up and down, electrons, and photons. So if we combine, for instance, two up quarks and one down, we get a particle with charge +1, and this is the proton with the corresponding spin. In contrast, if we combine only one quark up and two down, we get a particle free of charge and the same spin. So these are the nucleons, and the combination of nucleons and leptons, electrons, gives rise to atoms. Combination of atoms promotes the formation of molecules, from different molecules, supramolecules, and so on and so forth. And we have the photon. Nowadays, there's a renaissance of photochemistry, in particular, photochemistry involving visible light. So with nucleons, electrons, and photons, we can develop the entire chemistry, biochemistry, molecular biology, etc. So this description of matter, of known matter, concern physics and chemistry. So I find especially interesting and inspiring the kanji ideograms for physics and chemistry. So according to these ideograms, physics is the science of matter. The two ideograms for matter and reason or logic, and using physics, we describe the essentials, the composition, and the behavior of matter, the different properties, emergent properties, etc. Chemistry, instead, consists of the science of change. These are the ideograms for change and study. So, according to chemistry, we study the change from one given form of matter and its conversion into another one, into another different one. This transition, this change, can involve atoms, molecules, and even the nuclei of atoms. For instance, if we study the double beta decay process, according to this, one given neutron can be transformed into a proton by a conversion of one quark down to up, and the emission of one electron and one electronic antineutrino. So if we extend this process to two neutrons, we advance two positions in the periodic table, and we transform this nucleus in another one, in another element. In contrast, if we describe this process as a neutrinoless transition, here again the quark down is converted, is transformed into a quark up. So we transform the neutron into one proton, and if we repeat the process, we have two protons, two additional protons, and here again we move towards, we advance two positions in the periodic table. The difference is that in this case, if the neutrino is its own antiparticle, there's an annihilation here, and we only observe the emission of two electrons. This is the neutrinoless double beta decay process. So according to this scheme, the double beta decay with two neutrinos obeys the Dirac equation, but in this case, neutrino behaves like a Majorana particle and it's identical to its own antiparticle. This means that we can understand a little bit more the behavior of matter, especially in during the generation of novel particles. For instance, according to this scheme, the early universe had quarks and antiquarks. There was an annihilation between matter and antimatter. Antimatter disappears, and what we have, what we are now, with what our universe is now, is not the outcome of Big Bang, but the leftovers of the Big Bang. So this small asymmetry between matter and antimatter can be understood if we assume that in this case there's a neutral particle, the neutrino, which is a double agent and behaves as matter and antimatter. And this the final outcome is not the complete annihilation between matter and antimatter, but the remains of some matter that is the fundamental, at least as far as known matter is concerned. It's about 5% of the total matter of the universe, involves this asymmetry for neutrinos. So we can distinguish the double beta decay involving 2 neutrinos and 0 neutrinos by the energy of the electrons emitted as a consequence of these double beta decay processes. In the case of neutrinoless double beta decay process, the energy of the electrons is higher than that associated with the normal, say, double beta decay process involving 2 neutrinos, because these neutrinos have their own energy at the cost of withdrawing energy from the electrons. So we have a spectrum here for the double beta decay involving 2 neutrinos, and here a peak, an extreme peak associated with the neutrinoless double beta decay process. The problem with these reactions is that the kinetic constants are extremely low. So the half-life time is larger than the age of the universe. So the measurement, the detection of this kind of processes is associated and with an extremely unusual event. So in this respect, our only hope is to use the Avogadro's number, which is also pretty high. So we can expect to detect several events within a reasonable time, because this competition is unfair, because nature and the universe has billions of years to evolve, and we have several years to execute a research process. So somehow, in this case, the Avogadro's number is our essential tool to detect these extremely unusual events. So there are, along the periodic table, different double beta decay nuclei that can suffer this kind of processes. These different experiments and collaborations involve calcium atoms, germanium, tellurium, and xenon. And this is precisely the kind of disintegration the next collaboration is working with. So this process, remember, through this double beta decay process, we advance 2 positions in the periodic table. So we go from xenon to barium. Okay, so we need to detect 2 electrons and 1 barium dication. Okay, and this is the essentials of the next collaboration promoted by Professor Gómez Cadenas and Iker Basque research professor, and Roxane Guenet in Harvard and now in the University of Manchester, and Dave Nygren at the University of Texas in Arlington. David developed the concept of the basic design of this experiment, and Gómez Cadenas developed, and here Francesc Monraval, you can see Francesc Monraval as he's also an Iker Basque professor here at the DIPC, and the building of the detector is carried out here in the DIPC at the Center for Materials Physics and the University of the Basque Country. So in a sense, we are studying this process, and here you can observe the evolution of the different next detectors. And of course, for any question you can ask Professor Francesc Monraval, that he could inform you or give you much more details about the design and construction of these different detectors. This is, of course, an international collaboration, and the basic design consists of generating here of the camera. If we observe the disintegration of xenon 136, we should be able to detect the electrons, and this part corresponds to Roxanne's team at Manchester, and we chemists deal with the detection of the barium cation. This is the barium tagging. We are interested in the development, design, and development of the barium tagging detector. So if we analyze the evolution of the electrons, we can observe the drift and the energies of these electrons, this pair of electrons associated with a double beta decay process. And this part involves, say, the chemical part of the entire project. So we need to generate, to detect the drift according to the data provided by the electrons. We can detect the barium cation with a convenient fluorescent detector and the camera. So if we obtain a specific fluorescent signal associated with the capture of barium cation, and we correlate this detection with the energy and the evolution of these electrons, we should be able to detect without any ambiguity the correlation between these electrons and the barium cation, and hopefully the detection for the very first time the evolution of one neutrinoless double beta decay process. Okay, so now the main point is to develop, to design and develop these fluorescent sensors to detect specifically barium under high pressure gas conditions. Most of the supramolecular chemistry involves studies in solution. We chemists are very comfortable with solutions in different solvents, and in this respect, supramolecular chemistry, namely the interaction between molecules and analytes, in this case cations, is very well developed in solution. But the behavior of this kind of sensors in the interface between the solid and gas states is not very well understood nowadays. So the chemical part of this next bold collaboration involves different coordinators, Zoraida Freixa and Ivan Rivilla, who are Ikerbasque researchers, and different postdoctoral associates and PhD students. So the basics of the design of these fluorescent indicators involves the incorporation of one chelating group to incorporate the cation, in this case the barium cation, the fluorophore, one spacer, and one linker to bind covalently the sensor to a surface. Okay. So we can distinguish between different kinds of detectors. we have the fluorescent monocolor indicators or fluorescent bicolor indicators. In the case of monocolor indicators, we have the off-on or on-off detectors. But in the case of bicolor indicators, we have the on prime with blue shift and on prime red shift, depending upon the shift of the signal associated with the bound species of this fluorescent sensor. And the other collaboration of NEXT in Arlington, in Texas, they are interested mainly in this kind of off-on detectors. The issue is that remember that this is an extremely unusual, rare event. This means that the background produced by the sensor in its free state should be very, very large. So despite the very small signal of the sensor in the free state, this could be enough to hide the rare signal associated with the capture of the cation. This is the reason why we decided to test this bicolor indicator instead of the monocolor one, as we will see later on. So the basic concept is that if you have a monocolor indicator, the background generated by the sensor in its free state could be enough to hide the signal associated with the emission. Instead, we designed a bicolor indicator. The fluorophore has two components, and upon coordination with the cation, the second part of the fluorophore is disconnected from the main fluorophore. So we should observe different wavelengths at the free and bound states. And if the delta lambda shift is large enough, we can expect to obtain an essentially background-free signal for the bound state. Okay. So we designed this first generation of sensors that involves several synthetic steps to obtain the corresponding products. This is well, non-obvious synthetic route involving the formation of carbon-carbon bonds by means of organometallic reagents. But well, eventually we were able to obtain with acceptable yields the final products. And we measured the photophysics associated with the barium complexation of these molecules, and we observed that this one was the best one actually. Actually, the parent molecule, the simplest molecule, is the most effective one. Also, here you can observe the bicolor behavior of the sensor is green in the free state, and upon the barium capture has a blue shift, and we observe this dark blue emission at these different wavelengths, will essentially give rise to an essentially background-free signal. We measured the binding constant of this molecule, which was very high, is very acceptable for our proposals, because remember that this is an extremely unusual event. So this means that we need to capture every barium cation produced as a consequence of the double beta decay process. So we need to capture all the ions, the barium ions produced in this kind of processes. In addition, the Jobs plot of this molecule showed that every sensor, every molecule captures one and only one barium cation. Okay. And using this device developed by Pablo Artal and co-workers, we were able to detect the essentially background-free emission spectrum. Actually, I must confess that the editor said in our original title, we said background-free detection of barium cations, and he said, well, this is a much better low background detection. And yes, finally, it is a very low background, which is enough to distinguish between the free and bound state. For instance, here we have our sensor, which is quite the brightness of this sensor is pretty high. So if we observe the signals on the surface by means of the device designed by Pablo Artal, we observe a lot of signals corresponding to this green emission. Okay. And at this level, if we apply an optical filter here, every signal is removed from the image. So this is a signal-free spectrum for the sensor in its free state. In contrast, if we add barium, now we have a very intense area promoted by the mixture between this peak or this band and this one. But now if we apply the optical filter on the system, now we can distinguish the signals associated only to the capture of barium cations. Okay. So this demonstrates that this sensor can be useful or is at least promising enough for further developments. This is the structure of the molecule in its free state, in which this phenyl group is coplanar with the main fluorophore, and the behavior of this ensemble of aromatic groups is different to this one. Upon capture of barium, the crown ether interacts with the cation as we expected, but there's also an interaction between this nitrogen atom and the cation, and there's a pi cation interaction associated with this phenyl group, which is now almost orthogonal to the main fluorophore. So we need now we transform this fluorophore into only this one. So we observe a blue shift associated with coordination. Using NMR, nuclear magnetic resonance, we observe the shift of the signals of this phenyl group, thus showing that in effect, upon coordination, this group is participating in the interaction with the cation. And David Casanova and Claire Tonnelet, using time-dependent DFT calculations, they demonstrated now computationally that in effect the transition of the transition of the molecule at the free state involves this phenyl group here, but coordination with barium removes this part from the fluorophore that now is essentially this component. So everything is fine. And also we performed different simulations at different dihedral angles to confirm the evolution of the emissions depending upon the rotation of this second component of the fluorophore. And we observed the different geometries of these molecules at the ground state and the first excited singlet state. And we observed the one shift and the different intensities associated with the transitions at both states. And also we simulated the behavior, the possible translation of this behavior to an atmosphere involving xenon gas. And we observed that in effect, the main features observed calculated for the in vacuum experiments can be translated to the gas phase or the high pressure gas phase. And in addition, Celia Roguero, Pablo Herrero, and the co-workers at the CFM, they studied the behavior of this bicolour indicator on a gold surface, and they observed here at this solid gas interface the interaction of the among many other spectra and experiments. Celia and Pablo can give you much more detailed information about these experiments, but they also observed this behavior combining the experimental images with the calculated ones. And also we can distinguish here two different possibilities. If we translate the bound structure to the solid gas interface, we have this structure here, but there's another possible one in which the barium cation interacts only with the crown ether on the convex phase of the bicolour indicator. And here again, the two components of the fluorophore are almost planar. This could be a major drawback for the entire model, but we calculated this the energy of this other possible interaction pattern is much higher in energy. This means that if exists, this structure could be in ppm with respect to the most stable interaction pattern, which is similar to that observed for the in vacuum and solution studies. So there's still a lot of room for further improvements, and we in the next step of our research, we decided to explore different possibilities in order to get larger shifts in the emission spectra associated with the bound species, and also to observe higher brightness, larger discrimination factor, and bigger binding constant for the next generations of sensors. So as a first step, after performing extended vehicle simulations, we realized that the simple change of this nitrogen atom here, the inversion of the carbon and nitrogen atoms, should result in very interesting properties for this next generation sensors. In addition, we extended this second component of the fluorophore to an extended aromatic system. And we calculated within this tool box of components, we calculated the different combinations among these parts of the molecule. So this is the first generation in which we have the crown ether, the pi cation interaction, and the nitrogen cation interaction. In the next generations, we inverted the configuration of the system, and we extended different structures in order to see what happens, which are the possible coordination patterns of the dication to the sensor. First, we computed the structures associated with these novel molecules in order to make sure that the synthetic effort to obtain these molecules deserves further developments or not. And here we observe that, in effect, in this case, we could observe a similar behavior. A similar behavior with the crown ether, pi cation interaction, and nitrogen cation interaction. So we also extended this model to this biphenyl group here, and we observe that instead of this crown ether, pi interaction, nitrogen atom, the system prefers to interact with two aromatic rings, as you can see here, in very, very bent structure. But still, the interaction energy is large enough to justify the chemical synthesis of this kind of molecules. So we proceed with the chemical synthesis. As you can see here, this apparently extremely simple, even naive change of nitrogen by carbon involves a much more complicated chemical synthesis. So we developed this synthetic route. We tested different possibilities, but the most efficient one consisted of starting from this acyl chrome ether, and in order to obtain the functionalized boronic ester, also to develop, here are 5 steps. So this is a simplified model. This is important in order to physics realize that the chemical synthesis is complicated, uncertain, risky, and expensive and large in terms of time. Okay, so using this scheme, we prepare these precursors, and we obtained the different compounds with acceptable yields. And much to our delight, we observe that in effect, all these molecules are, as predicted by the calculations, bicolour in nature. And this is, for the sake of comparison, the behavior of the first generation we have already discussed. This is the second generation, which the colors are different, but the delta lambda values are even higher than in the first case. In addition, here, the intensity of the emission spectra of the free and bound states are similar, which is not very convenient in order to detect this extremely rare event. But here, the intensity of the free molecule is much lower than that associated with the bound state. So we thought that this is a very promising starting point. And also, in the case of the biphenyl group here, we extended, remember that now we have crown ether, phenyl interaction. The intensity of the bound state is lower than that associated with the free state. And for the fourth generation, we have a comparable, slightly lower intensity for the free state, but the separation of the emission spectra is lower than in this case. So we analyzed in detail the different properties, the photophysical properties, and we concluded that this compound is the most efficient one, even more efficient than the first generation in terms of quantum yield, delta lambda values, brightness, and especially the binding constant. Remember that for the first generation, we obtained this value, and the constant associated with the second generation is 2 orders of magnitude higher than the first generation. So the probability of capturing the barium cation is 2 orders of magnitude higher with respect to a previously higher value. Okay. And we also performed simulations in order to reproduce the ultraviolet absorption spectra, and we concluded that this DFT functional was the most effective one. And also we computed the theoretical values for the barium capture for this second generation species, and the experimental value is about 70 nanometers, and using different functionals, we evolved between 89 and 32 nanometers, which is quite acceptable in terms of accuracy for the description of these sensors. So remember that till now we have developed the chelating group and the fluorophore. We need to install into this sensor the spacer and the linker. To do this, we transformed this starting molecule into this group. This molecule that involves this amide spacer and silatrane group that is the linker to other species. So here we can anchor our sensor on quartz or ITO on the surface. After washing and neutralizing the surface, we obtain this functional surface with the covalent interaction between the sensor and the surface, the spacer, and then the fluorophore, the first component, the second one, and the crown ether. Okay, so we computed the geometrical properties of this compound on the surface, and we were able to obtain the optimal conditions for an homogeneous monolayer of incorporating our sensor. And using this scheme, we have obtained not too bad emission spectra for the bound compounds. We have still 88 delta lambda values, but the brightness, the sensitivity of the measurements is lower than in the previous cases. So we are studying different surfaces, different spacers in order to optimize this value. But at least the behavior, the translation from the solution chemistry to the solid gas interface supramolecular chemistry is still possible. Of course, there's still room for further developments. So In conclusion, we have developed these bicolour indicators that can be useful for as barium tagging components in neutrinoless double beta decay processes. The first generation was actually useful, both in the solid and liquid state and on surfaces, etc. But the second generation is still very promising one. And of course, other alternative generations are under study in our labs, and we are convinced that there's still room for further developments. But as a conceptual guide for the further developments and designs, DFT and time-dependent DFT are very useful tools for assisting this novel design. So we can rely on calculations, and then if the results are promising enough, we can go to the lab and prepare the designed compounds. I would like to thank these institutions for the financial support and to all of you for your kind attention. Thank you very much.
Wonderful talk and impressive results. So, time for questions.
Nice talk. I like it very much. I have a question on the pre-detection. So in the production of the double beta decay, the question is about the xenon. How much xenon will be used in the experiment, and is that natural xenon gas or enriched special isotope?
Yeah, it's a special isotope. It's xenon 136, and the different developments involve different quantities of xenon inside. The idea is to use 1 ton of this 136 xenon, but Francesc can give you much more details about the next generations of and also the detector which is currently under development in Canfranc. If you want, Francesc, we can give more details.
We enrich xenon at 90% this isotope. And the current detector that will start running in 2023 will have 100 kilograms of this. And the idea for the detector where we want to implement the
Barium
tagging is to use at least 1 ton of xenon. It's basically because of what he was saying at the beginning, because the lifetime we want to explore are around 10 to 27 years. So even if the Avogadro number is very high, you still need 1,000 moles of material.
Hopefully.
Yeah.
Thank you.
Questions? Yeah.
How do you know this lifetime experiment? The calculation. How reliable is the value?
Well, okay. Yeah, I mean, we can discuss that. I mean, please ask questions about chemistry.
We are among physicists, so that's really the point.
I mean, you put some amount of material and you take it for a while. If you don't see results, you put a limit of the life. That's basically what you measure. The measuring limits.
But there was never ever a single decay like that detected. So I mean, you have.
Yes, that's why we put limits.
Yeah. Actually, instead of measuring the half times, you measure the limits of these values. Between this value and the other one. By now, as far as I know, there's no an exact measurement of the kinetic constant for this double beta decay process. There are only limits.
So it means, I mean, you have to have some hope also that it actually happens.
Yeah, well, I mean, but now they don't have time to put that in a plot, but theoretically, we expect that to be in some range of lightness. The tone scale will be the next hole where it will be. If it is not there, then we may need to go to 50 tones, 100 tones. It's a different again.
We used to say the situation is hopeless, but not serious.
Are you considering also other types of fluorophores?
Yes, we are
Not
studying
based on
other
this
types.
specific.
Yes, we are considering other types, but we are still at a very, very preliminary stages. I have shown the fluorophores under development. The good news that the second generation has demonstrated to be better than the first one. So we think that we could improve even more the photophysics and the supramolecular chemistry of the other generations. The point here is that there's always the risk of going to a monocolor indicator. So if you have very over-designed, say, sensor, the behavior of the sensor is not flexible enough to yield a bicolor indicator. So if one conformation, say, is very, very stable, even upon capture, the rest of the system remains essentially unchanged. And this means that you are going to a monocolor indicator. So you need to deal with, to achieve some kind of trade-off between strong interaction and flexibility, which is not so easy.
Related to this, if I picked up correctly, the first generation and the second generation are very similar. The difference is in the orientation of one group with respect to the other. Is that right? Or my question is, what is why is the difference in the binding constants between the first generation and the second generation?
Yeah,
That's internal strain within the molecule.
no, is the electron density is delocalized differently in the two generations. Even this naive inversion of carbon nitrogen involves a much more complex synthesis, but in addition, the electron density of this nitrogen atom is higher in the second generation. This means that other factors remaining essentially the same, more or less. The superior coordination ability of this atom
Of
means,
nitrogen.
yeah, of nitrogen gives rise to 2 orders of magnitude, because we must remember that the relationship between concentrations and energy is exponential. So a couple of kcals per mole would involve 100, or in terms of concentration of the concentration of the different species. So even this change contributes to focus the electron density of the nitrogen atom, thus improving the coordination ability of the sensor. Yeah.
Thank you for the nice talk. I'm curious about the last part. I have I'm doubting about the conformation of the molecule when it is linked on the surface. How do you prevent the fluorophore from touching the surface? Is it freestanding like this?
Yeah, actually, we are developing different surfaces. If you assume that the sensor is a tree, we can put grass around the tree in order to maintain the system in the appropriate conformation and configuration, thus preventing the bending of the molecule and the absorption of the molecule on the surface, like in the system developed by Celia. We think that playing with the concentrations of the sensor and eventually on the different grass component, we can still preserve this situation of the molecule on the surface. Actually, this design is inspired in integrins. Integrins are adhesion molecules that have an open conformation and a closed conformation on the cell membrane. So the trick to get the open conformation is to put another subunit that keeps the integrin in this open conformation. And this is the basic idea that we translated into this inorganic or non-bio surfaces.
Actually, just the linker alone can act as the grass.
Yes, yes. Actually, the grass are these cyanotrains with 1, 2, 3, or even more carbon atoms, an inert, non-fluorescent molecule. So actually, yes, you're right. This is the leaves that we are putting on the surface. Yeah. The preliminary results are ambiguous. In some cases, it looks like the behavior of the sensor is not better than the behavior observed here for the isolated sensor. But of course, there's a lot of work to do to reach the optimal conditions.
Yes. Thank you very much for very nice talk. So you commented before that you're gonna use like 1 ton of the gas. So how much of this molecule do you have to use in the final design to this work?
Yeah, it all depends. The idea is not to install a homogeneous panel in surface in one part of the detector, but to put a robot, and if electrons move much faster than barium, barium is very heavy, so this means that we have enough time for Roxanne to determine the energy and the drift of the electrons. From that drift to the new trajectory of the barium cation, and we can put the sensor at that point. Yeah, so we think that we'll be able to move the detector fast enough to capture the barium cation. But I will say whether this is possible or not. According to particle physicists, a millisecond is the eternity, so there's no problem. We chemists are more skeptical about this, but yeah, in principle, it can be done. Yeah. Oh yes.
Oh, I think there is no questions from people following via Zoom, so let's thank Fernando once again for this very nice talk.